Okay, right. Good morning, everyone. I'm just trying to see if some other people are trying to join so I can admit them into the room. But I've started recording and it's 10 o'clock, so we can start and then the others who are trying to join can catch up. Right, so firstly, yeah, it's Friday. I hope you received the email I sent quite late last night. I'll run the review workshop face-to-face today. So that will be the first time we'll have that face-to-face review workshop. But yes, I've said in the email I've sent out, I realized that some people might want to join the review workshop, but they might not be able to come onto the campus. So I'll also do that live streaming via Zoom. So if you cannot come to campus, but you want to attend the review workshop, then please access the Zoom, the same Zoom room that we are using for our online classes. I plan to talk about, in the beginning, I plan to talk about the solutions or the answers to the first mastery test. And maybe, yeah, we'll go from there if there are questions or anything else that the students or you want to discuss. All right. So this is lecture 8 of 124103 Biophysical Principles. We will still continue with what we've been talking about with motion and forces. But this time we'll round off the Newton's laws of motion by talking about the third law. It's Newton's 3 laws of motion. So we've talked about the first and second laws. Today we will talk about the third law. So it's still related with forces, related to forces. Yeah, and because Newton's laws describe the connection between forces that act on the object and the object's movement. Yep, so we've already learned Newton's first law of motion. It says that if the net force is 0, yeah, net force is 0 means that the acceleration is 0. If the object is at rest, it will remain at rest. And if the object is already moving, it will move with constant velocity, meaning the same speed and in the same direction, so that acceleration is 0. So we looked at Newton's first law already, and then last time we looked at Newton's second law of motion that directly relates the net force to the amount of acceleration that a mass can have. So third law of motion, it's also called the law of interaction. It says that whenever an object exerts a force on a second object, the second object exerts an equal magnitude and opposite direction force on the first. And the text below is the more commonly found statement for the third law of motion. The key things here is that the reaction is opposite in direction, but equal in magnitude. So that's why it's called the law of interaction, because there are two objects that are interacting with each other. One object will exert a force, say object A and object B. Object A will exert a force on object B. In return, object B will exert a force on object A, and that force, the forces will have equal magnitudes but opposite directions. Right. So third law of motion is what makes walking possible. So consider in this figure here, a woman that's walking. So the woman's foot is pushing on the ground, okay? And the push force has a direction of to the left. So the foot pushes on the ground to the left. Okay, the reaction to this action force would be the ground pushing the foot to the right. Okay. So you can see there are two interacting objects, the woman's foot and the ground, right? So the foot is exerting a force on the ground. The direction of that force is to the left. And in response to that, the ground pushes the woman's foot, and the direction of that would have to be to the right. And that the ground's push is what causes the woman to move forwards, essentially making her walk, right? Okay, so equal magnitude, opposite direction. Yeah, and so you can see Newton's, so this example of the woman walking, because of Newton's third law of motion, any movement we can see in nature would be a consequence of Newton's third law of motion. So propulsion of fish through water. Okay, so the fish pushes the water around itself. In return, the water pushes the fish with the same force, but in opposite directions, right? So flying motion of birds, walking, propulsion of rockets. So yeah, movement in general is a consequence of Newton's third law of motion. Yeah, so the key thing, because yeah, it's a law of interaction, you have two objects that need to interact. So to identify the action and reaction in Newton's third law of motion, you first have to identify the interaction. You have to identify which two objects are involved in the interaction. Okay. Once you identify the two objects, then you will be able to state the action and reaction forces. Yeah. So for example, the action is that object A exerts a force on object B. The reaction will still involve the same two objects. It's still object A and object B, except that for the reaction, it's the object B that's exerting force on object A. So it's the same two objects, but just the direction of force is interchanged. Okay, so for example, here in the first figure, you have a baseball that pushes the glove to the left. Okay, so you have there your two things, the baseball and the glove. What would be the reaction force to this action force? So this is the action force. The action force is that the baseball pushes the glove to the left. What would be the reaction force for this interaction, according to Newton's third law of motion? Yeah. So again, feel free to type your responses on the chat box. Yeah. So the ball will probably stop moving if the player catches it. Okay, so that would be another force. The reaction force, yeah, the glove pushes against the ball. Yeah, that would be the reaction force. It's just the two objects, baseball and the glove, but this time you interchange the order of the objects. In the action force, it's the baseball that pushes the glove. In the reaction force, it's the glove that pushes the baseball. And notice the direction is to the right. Right. It's not necessarily that the glove will stop the ball from moving, because if let me just see if hopefully you can see. Yeah, so imagine this is the glove and this is the baseball. And maybe I should remove my background so you can see the demonstration. Yeah, okay. Right, so say this is the glove and this is the baseball ball, which is not so obvious against the white background there. Okay, notice that if it does not necessarily stop, the glove does not necessarily stop the ball. Yeah, so notice how the eraser, the rubber in this case, bounced off my hand. Right, so the action force there would be the rubber pushed on my hand, and in response to that, my hand pushed on the rubber, and that actually caused the rubber to bounce back. So it's not necessarily that the hand or the glove will stop the ball, right? So I hope that clarifies that. Okay, for the second case, you have three objects. You have 2 feet, foot A and foot C, and then you have the ball. So you have 3 objects here. So how do we apply Newton's third law of motion if you have more than one object? Okay. So remember that the interaction is just between 2 objects at a time. So you'll have to divide the complex scenario and just look at 2 objects at a time. So here, for example, the first action force is that the foot A pushes the ball B to the right. What would be the reaction force to this action of the foot A pushing the ball to the right? Yep, equal and opposite. That's correct. So it will now be the ball B pushing against the foot, right? And the directions are opposite. Okay. And similarly for, so that's the reaction. And similarly for the action of the foot C pushing the ball B to the left, it will be, the reaction will be ball B pushing the foot to the right. Yeah. So it's always 2 objects that are interacting, and then you make the directions of the forces opposite. Okay. Right. So Newton's third law of motion is usually just statements. it's the one we don't have to calculate anything. So if something will be asked in the test about Newton's third law of motion, it's mostly conceptual. Right. So it's action reaction acting on different objects. So just some things I want to emphasize. The action and reaction forces never cancel each other out because they're acting on different objects. Yeah. Object B and object A, or the ball and the foot, they're 2 different objects. And when you draw your free body diagram, you're drawing forces just on a single object. So we do not include the reaction forces in the free body diagram. Right. So I just wanted to emphasize that. But yeah, that essentially, this is a short video clip that illustrates Newton's third law of motion. So maybe, yeah. Can you hear the sound? If you can give an indication of whether you can hear the sound. No, okay. So let me see. Let me just adjust the sound. Oh. Let me just stop sharing my screen, and then I'll adjust the sound of this thing. Share my screen. So can you hear the sound now? Is the sound?
I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law.
Yeah, okay. Let me just start that.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between 2 objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. Going to be object 1 on the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
It's quite cool to see that in action, isn't it? We don't really think about Newton's third law of motion when we're moving on Earth, but seeing it that way sort of hopefully clarified the concept of Newton's third law. Right. So before we proceed, are there any questions about Newton's third law or first or second law or right? Nope. Okay. So now that we've learned the three laws of motion and we've been talking about forces and drawing free body diagrams, and that net force and how to get the net force given several forces, we'll now put everything together, and that's why we call it problem solving, because this is where we put everything together, drawing the free body diagram, finding the net force, and applying the laws of motion to solve some problems, right? So just some quick tips. So that's why we've been going through these individual steps actually in our previous lessons. So the first step is always to draw a free body diagram. So that's really the starting point. Because your free body diagram allows you to visualize all the forces that are acting on the object. And a correct free body diagram would be the most important step. Okay, and then once you draw your free body diagram, choose your X and Y axes. Usually the X axis is in the direction of motion. Usually choose one axis to be in the direction of acceleration, and we'll see examples of why that's important. For example, movement along an inclined plane. And then you assign the positive and negative directions. The convention we're using is to the right is positive, upwards is positive, to the left is negative, and downwards is negative. So assign where is positive and negative, because that influences whether your force is negative or positive, right? If your force is pointing to the left, for example, then you should have a negative force. So that's the second step. And then third step is when you apply Newton's second law of motion. Because Newton's second law of motion now relates the net force to the acceleration. Yeah, so you apply Newton's second law of motion along two axes, along the horizontal and along the vertical. So that's why in our previous lectures, we were getting the net force along the horizontal or along the x-axis. independently from the net force along the vertical or along the y-axis. Okay, so you independently get the net force along the horizontal, find the acceleration along the horizontal because of that net force, and then independently get the net force along the vertical, and then get the acceleration along the vertical because of that net force. And remember that if your object is at rest or if it's moving with a constant velocity, then acceleration is equal to 0. And then finally, once you've set up Newton's second law of motion equation, F net equals mass times acceleration, then you can solve whatever's being asked. If you're being solved for the acceleration, then you can rearrange the equation. Acceleration is equal to net force over mass, for example. And we've seen how to rearrange that in the last lecture. And you can just put this in your formula sheet if you want. Acceleration equals net force over mass. Okay, so let's start looking at example problems. Here is a person who wants to push a cart. And the question says, how hard should you push your cart for it to accelerate from rest to 0.25 meters per second squared? So notice the unit there is meters per second squared. So acceleration is already given, although it states the initial velocity, which is 0 from rest. And the direction of acceleration is to the right. Okay? The cart and its contents has a mass of 20 kilograms and explicitly stated is ignore friction and air resistance. Okay, so let's go through the steps that I've outlined earlier. First one, identify the objects, draw your free body diagram and identify which is positive and negative directions, then apply Newton's laws of motion, Newton's second law of motion. Right, so what is the object in this case? Which is the thing that experiences the forces that we need to draw the free body diagram of? It should be the cart, right? Good, it's the cart that you want to push. Okay, right, so can you give me one force? We'll draw now the free body diagram because once you've identified your object, the next step is draw your free body diagram. So can you give me one force that's acting on the cart? Weight, very good. Yeah, it's the easiest force of all. Whenever you have mass, you'll have weight. What's the direction of the weight force? It's always downwards, right? Okay, any other force acting on the cart? Yes, the ground is supporting the cart. Good. What force is that? Yeah, it's upwards because we'll assume the ground is level and this force here. What's the name of the force that's exerted by the ground that supports the objects? Normal force. Good. It's always perpendicular to the surface, so that's why it's upwards. Okay, any other force acting on the cart? How should the cart move to the right? Pushing, very good. Yeah. So in order to notice these two forces, normal and weight force, they're along the vertical, but the cart is moving to the right. So in order for the cart to move, it says here that you're pushing on it. So there should be a push force to the right. And you can just label that as push, F push. Right? So that's, yeah. So here's a neater drawing of the free body diagram that we just did. And we identified now the acceleration is to the right. Your cart wants to move to the right. So we identify to the right is positive, upwards is negative. Okay, so once you have your free body diagram, you can already see which force is along the X or horizontal and which forces are along the vertical. You now apply Newton's second law of motion. Yeah, it's this equation, net force is equal to mass times acceleration. Okay, we want to find the push force, how much force should you push the cart? And if you look at your free body diagram, the push force is along the horizontal or along the x-axis. And that therefore we need to apply Newton's second law of motion along the x component or along the horizontal. So if you do that, the net force along the x-axis or along the horizontal should be equal to the mass times the acceleration along the horizontal or along the x-axis. Okay. Starting from this Newton's second law of motion, it says net force. And so that's where you have to go and look at your free body diagram now to determine what are the forces along the horizontal. And you can see there's only one force that's along the horizontal, right? It's the push force. Okay. So the net force, there's only one of that. It's only the push force that's along the horizontal. So this is the left-hand side. The right-hand side, it's still the same. Right-hand side of the equation, it's still mass times acceleration along the x. Okay. Yeah, we are given the mass. The mass is given to be 20 kilograms and the acceleration was given. Therefore, you can calculate the push force. Yeah, and I deliberately put the units, the mass was given in kgs and the acceleration was given in meters per second squared. So that automatically gives you a unit of newtons for the force. So just be careful with units here. Your units should be in base units. If the mass is given in grams, you have to convert that to kilograms, right? And your acceleration should be in meters per second squared. All right, so that's how you apply Newton's second law of motion. Look at one side of the equation one at a time, okay? Net force, and then look at the right-hand side, mass times acceleration. Okay. Right, just for demonstration, if you want to apply Newton's second law of motion along the y-axis, okay, so the problem has already been solved. We already solved for the push force which being asked, but if you want to find the force along the y-axis, I'll just demonstrate how we apply Newton's second law of motion along the y-axis. You need to get the y components of Newton's second law of motion, meaning look for the net force along the vertical, and that would be equal to the mass times acceleration along the vertical. Okay. So again, work at this equation one side at a time. Let's do the left-hand side first, which says net force. Look at your free body diagram. What are the forces along the y? You have the normal force and the weight force. Okay, we said that upwards is positive, downwards is negative. Therefore, your normal force would be positive. So, yeah, strictly speaking, there's a plus n there because your normal force is positive. But yeah, if we're writing the equation, we don't really put the plus sign if it's the beginning of the equation. If there's no plus sign there, it's assumed that it's a positive normal force, and then you have the negative weight force that's pointing downwards. Okay, so that's the left-hand side of Newton's second law of motion. Then the right-hand side, it's still just carried over. Okay, right? What do you think is the acceleration along the y? Yeah, 0. So we can assume that the cart is just moving to the right. So we can assume that it's not jumping up and down. Okay, so it has no acceleration along the y. And so acceleration along the y is 0, and your Newton's second law of motion becomes normal force minus weight force is equal to 0. And from that, you can rearrange this equation to find the normal force. Yeah, to find the normal force, you want to isolate the normal force. So you do the reverse operation of the minus weight. If you add plus W or plus weight on both sides of the equation, you have minus W plus W will give you 0. And so you have your normal force is equal to the weight force. And you can calculate your normal force from the definition of weight force being mass times gravitational acceleration. And you can get a value for your normal force. right? Okay, are there any questions about this before we go to, so we started with something simple just to demonstrate Newton's second law of motion, and we'll work towards getting more and more complex problems. So at this point, are there any questions or not yet? Good, all right, okay. Now let's make it a little bit more complex and add friction. Okay, so the ground, so it's the same problem in black here, black font, but now we add the complication of frictional force. So the ground exerts a force N that opposes 2 newtons that opposes the motion. So opposes, that gives you a clue that it's frictional force that's added here. It's still the cart that's being pushed, so it's still the object. So everything, the free body diagram is the same, except that you have this added friction force, and the friction force is opposite the direction of motion. That's why it should be pointing to the left. Cool. Right, so we have our free body diagram. That's the starting point. We now go to Newton's second law of motion. Again, we do second law along the x component and then along the y component independently of each other. Right, so along the x component, let's look at the left-hand side of Newton's second law of motion. It says net force along the x or along the horizontal. Look at your free body diagram. You have two forces along the x. You have F push and you have friction. Okay. We defined that to the right is positive. Therefore, your F push should be positive and your friction should be negative. Okay. So that's the left-hand side there, expanded to include all the forces along the x-axis, and then your right-hand side is still mass times acceleration along the x. All right, we want it's still the acceleration that we want to find, right? It's how hard you want to push, so it's still the push force that you want to find. So you need to rearrange this equation to isolate F push. Okay, so that means you need to get rid of this minus F equals MAX. Yep, so you can use the method we learned about building up the equation and then tearing it down. Or if it's just a minus sign here, do the reverse operation to cancel out this minus sign. The reverse of minus is plus. So if I plus F on the left side, I also do a plus F on the right side. And adding plus F to minus F cancels out this to the friction force on the left side. And so you have, oh, I actually have it there. So let me erase my writing. Yeah. And so you have F push is equal to mass times acceleration along the X plus the friction force. Okay. And we know everything because we're given the mass. It's 20 kgs. The acceleration we want to achieve is 0.25 meters per second squared. And then we're given the actual frictional force. It's given in newtons already, 2 newtons, which newtons is kilogram per meter squared also. So you have a push force of 7 newtons. All right. Okay, so far are we okay? Good, all right, I can see some thumbs up there. Good, right. Okay, now let's go to something, this is just demonstrating again along the y component. We've actually already solved the problem, but we'll see how the y component changes if we add the friction force. So we start with Newton's second law of motion along the y. Net force along the y is equal to mass times acceleration along the y. We look at the forces along the y, you only have normal force and the weight force. Just as before, you have normal minus weight force. Left-hand side and right-hand side is mass times acceleration. We already said that the acceleration along the vertical is 0. right? The cart's not jumping up and down. So your normal force is still equal to your weight force, just as we've seen earlier in the no friction case. So you can see here, that the normal force is still 200 newtons, the same as what we had when there was no friction. So you can see here that the friction did not affect, right, the forces along the Y, because the friction was along the horizontal, whereas the normal force and the weight forces were along the Y. Okay? And that's why we need to separate the analysis along the horizontal from the analysis along the vertical. Okay, and we always often have to write Newton's second law in two forms: X component and Y component, and never combine forces along the horizontal with forces along the vertical. They should be separate. Okay, right. So let's go to a little bit more complex example now. You have a 10-kilogram package. It's being pulled along the floor with a force of 40 newtons, but that force is applied at an angle of 30 degrees. So you're pulling on this object with 40 newtons, and you have an angle theta of 30 degrees. In short, you have this diagonal force that's acting on the object, on the 10-kilogram package. You want to find the acceleration of the package, and then what's the magnitude of the normal force exerted by the floor on the package. Right, so let's go through the steps again. It's the systematic steps. Right, we have to identify the objects, and it says what's the acceleration of the package. So obviously your object is the package. It's what's experiencing the forces. Draw the free body diagrams. Okay, any object that has mass will have weight. Okay, and then any object that's supported by a surface will have a normal force, just like we've seen in the first example. Okay. And then, as I've drawn in the figure there, you have a pulling force that's at an angle 30 degrees. Okay. Right. So I hope last lectures coming back, you have this diagonal force. It might be a traumatizing lecture. I've got feedback that it was a difficult topic. But you have this diagonal force, this F pull force. And last time we learned that whenever you have a diagonal force, you have to break that down into its horizontal and vertical components, right? Okay, so you have the horizontal component of the pull force and the vertical component of the pull force. So notice how we draw the horizontal and vertical components. The tail of the vertical meets the head of the horizontal. Okay, and your net force goes from all the tails to all the heads. Okay, so you need to get the X and Y components of the diagonal force. Once you get the X and Y components, you can get rid of the diagonal force. Okay, so the reason why we are breaking down the diagonal force into its X and Y components is because once you have the X and Y components, you can forget about the diagonal force and you can get rid of it. And as you can see in your free body diagram, you only now have forces along the horizontal and forces along the vertical, which is easier to analyze rather than forces along the diagonal. Right? So the acceleration is to the right. So you identify which direction is positive and negative. And then you can work out Newton's second law of motion. Net force is equal to mass times acceleration. So let's do the X component. So that's the net force along the X, and that should be the acceleration along the X. Look at your free body diagram. you only have one force along the horizontal, which is the x component of your pulling force, right? It's F pull cosine theta. Right? So there's only one net force, the x component of your pulling force, which is F pull cosine theta. Right hand side is still mass times acceleration. Yeah. So, oh, why did my ink? So the net force is that, acceleration was just carried over. Okay, we're given the mass, we're given the pulling force, the angle, and gravitational acceleration, which we need for the weight later on. But essentially, yeah, we need to solve for acceleration. So we need to rearrange this equation to find the acceleration. That means we need to get rid of the mass on the right-hand side in order to isolate acceleration. So you do the reverse operation. So acceleration is tied to the mass via a multiplication. So you have to do the reverse of a multiplication to get rid of the mass. If you divide this with the mass, you have to divide also the left side with the mass. And we know that a number divided by itself, or something divided by itself, is equal to 1. Mass divided by mass is equal to 1. And so that can just cancel out. And you have acceleration is equal to F pull cosine theta divided by mass. Okay. You know everything because the pulling force is given 40 newtons times cosine of the angle. The angle is given 30 degrees. And the mass divided by mass, the mass is given 10 kilograms. So you can solve for the acceleration. Yeah. So you do cosine 30, multiply that with 40 newtons, divide that by 10. You should get 3.46 meters per second squared. All right. Any question about this this problem? I think the trickiest bit here is breaking down the diagonal pull force into its x and y components. Yeah. And as long as the angle is measured relative to the horizontal, the x component will be this cosine theta. Force times cosine theta, and y component is the force times sine theta. Right? And then once you have only horizontal and vertical forces, just apply the same method, the same procedure that we did for the cart example. Okay, let's look at the second question. What is the magnitude of the upward force, normal force exerted by the floor? Okay, so we already had this free body diagram from before, where we broke down the pulling force into its x component and y component. But this time, the normal force is along the vertical, so that means we need to apply Newton's second law of motion along the vertical. Net force along the y, or along the vertical, equals mass times acceleration along the y. Okay. How many forces should you consider for the net force along the y? Three, correct. Looking at your free body diagram, you have 3 forces along the y. So don't forget there's the y component of the pull force. Okay, yeah, positive is upward. So you have the pull, F pull sine theta should be positive, pointing upwards. That's the y component of the pull force, plus the normal force that's upwards as well, and minus the weight force. And then the right-hand side is mass times acceleration along the y. We want to find, yeah. So what's the acceleration along the y in this case? We'll see if we can simplify this equation. It should be 0, right? Your package is just moving along the floor. If you pull your package, and it will move along the floor. Yeah, I know you might think that the package might be slanted a little bit, but usually to simplify things, if we say that the package is pulled along the floor, even if it's an angle, we are assuming that it's not bouncing up and down. So the acceleration along the y would be 0. In this case, let me just tidy up. Acceleration is equal to 0, so we can simplify this. F pool sine theta plus n minus w is equal to 0. Okay. And then we want to find the normal force, so we need to isolate the normal force. Okay. By doing the reverse operation. So it's tied with minus w. So if we plus w on the left side, we also plus w on the right side. And then you have a plus f pool sine theta. To get rid of that, you subtract minus f pool sine theta, and you do that on the right side as well. Minus f pool sine theta, and you have the rearranged equation for the normal force to be equal to the weight minus f pool sine theta. Right? Because weight will cancel on the left side, f pool sine theta, they will also cancel each other out. Right, so we can now solve everything because we know, yeah, weight is equal to mass times gravitational acceleration. So recall weight is mass times gravitational acceleration. The mass is 10 kgs, gravitational acceleration 9.8. F pool is given, and then sine 30 degrees. All right. Okay. Any question about this? Are we okay with this example? Yeah, all right. Okay, there's some thumbs up there. So maybe we can move on to the next. Yeah. Right, so now let's look at this inclined plane problem. A skier with mass of 58 kgs goes down a slope, and the slope has an angle of 25 degrees. There's frictional force that's 70 newtons. Calculate the net force acting on the skier in the direction of the motion, and therefore calculate the acceleration of the skier. Okay, it's obvious that the skier will go down the slope, so your acceleration should be along the slope here. So let's analyze this problem. It looks a bit complicated because now you have a normal force that's not vertically upwards. But let's go through the step-by-step procedure that we've been applying. Again, first step is to draw your free body diagram. Yeah. Okay. The simplest, anything that has mass will have weight. Weight is always downwards. Okay, the slope is supporting the skier, so there's a normal force. What's the direction of the normal force here? Should I draw the normal force vertically upwards, or should I draw it with some angle? Yes, yeah. So the normal force is always perpendicular to the surface. Okay, so there should be a 90-degree angle between the surface and the normal force. So yeah, vertical normal force is incorrect. So let me take that away. Okay, and then the problem explicitly says that there's frictional force. Frictional force opposes the motion. We know that the object will slide along the slope downwards, and so therefore your frictional force should be along the slope, but opposite the direction of sliding down. Right? Okay, so that's our free body diagram. Okay, anything that's on an inclined plane, this is the solution we're doing here is sort of a recipe for solving any problem that's on an inclined plane. So notice that in your free body diagram, the weight force, because now the weight force creates a right angled triangle together with the angle of the slope. Yeah, this is 90 degrees. The angle between the weight force and the base of the slope is 90 degrees, so that the weight force and the slope sort of creates this right angled triangle. And this is sort of a important realization because it will allow us to simplify this angle. The always a difficulty with working with inclined planes is how to deal with this angle of inclination, this 25-degree slope. Okay, but by realizing that actually the weight force creates a right angle together with the slope, we can find the angle between the weight force and the slope. Okay, so what do you think is the angle between the weight force and the slope? What is this angle here between the weight force and the slope? Any idea what that angle should be? Good. Yeah. Why is it 65? Yes, correct. That's correct. It's 65 degrees. Let me just tidy up my drawing here. Why is it 65 degrees? Correct. It's 180 minus 25 minus 90 because the angles of any triangle should add up to 180 degrees. Okay, so this is a fact, a mathematical fact that's useful to know. In this case, the angles of a triangle should add up to 180 degrees. Okay. Right. So once we've analyzed that, we can our free body diagram will now look like this. Yeah, you have your normal force that's perpendicular to the slope, the weight force that's directly downwards, and the frictional force that's along the slope but in the opposite direction. We usually put the x-axis along the direction of motion. Okay, that's why, with the cart is moving to the right along the horizontal, so your x-axis is the horizontal. Once you incline the plane, the object will slide down the plane. It's useful to assign the x-axis along the direction of the motion of your object. So we have now, instead of a horizontal x-axis, we have this diagonal x-axis. Okay, and we've determined earlier that the angle between the weight force and the x-axis is 65 degrees. This is sort of like the slope of the incline. We make the slope to be the x-axis, to be along the x-axis. Now, it's hard, I don't know about you, but it's hard to visualize, this slanted axes, x and y axes. So you can always rotate your axes, right? Keeping everything together. You can always rotate your axis so that your x-axis is in the horizontal and your y-axis is in the vertical, right? Right? Does that make sense? Why we rotated? Yeah. Does that make sense so far? Yeah. Right, so we just rotated this this figure with a diagonal x-axis to one where we have a horizontal x-axis. Okay. Right, the y-axis is along the normal force, because we know that the x-axis and the y-axis should form a 90-degree angle. They should be perpendicular. So if you put your x-axis to be along the slope, then the y-axis should be perpendicular to that, and the normal force is also perpendicular to the slope, and hence the y-axis is in the same line as the normal force. Okay, now our free body diagram is showing us that we have a frictional force along the horizontal, a normal force along the vertical, and then we have now this weight force that is diagonal. You once again have this diagonal force that is at an angle of 65 degrees relative to the x-axis. And so just like the problem of the package being pulled by a string that is at an angle, we have to get the x and y components of this diagonal weight force, right? Yeah, so we have to get the x component of this weight force, the component along the x-axis, and also the y component of this weight force. Okay. Right, so you can see the logic here why we, instead of using this 25-degree angle for the slope, we tried to find the angle between the weight force and the slope, because then that angle between the weight force and the slope is actually the angle between the weight force and the x-axis. Okay. And that makes it simpler to get the x component and the y component, because we know that if the angle is measured relative or with respect to the x-axis, the x component will always be a cosine theta function multiplied to the diagonal force, and the y component will be a sine theta function multiplied with the diagonal weight force. Okay, right, so the x component of the weight force is the weight times the cosine of the angle relative to the x-axis, which is 65 degrees. And the y component is the weight force. Oh, yeah, I expanded it there now. Recall that weight is equal to mass times gravitational acceleration. These two together is actually the weight force multiplied with sine 65 degrees. Right, so that allows, so once again, we're getting the x and y components, because once you have your x and y components, you can get rid of the diagonal force. You can forget about it. Yeah, it's such a horrible, complicated diagonal force, but you can get rid of it by getting the x and y components. And look at your free body diagram. You only now have horizontal and vertical forces, which are easier to analyze. Okay, so yeah, the weight force along the x, yeah, recall weight is mass times gravitational acceleration, because we're given the mass of the skier. Okay, the mass of the skier was given as 58 kilograms. Gravitational acceleration is constant, 9.8 meters per second squared. Then you have the cosine of the angle. Okay, remember that we're getting the angle relative to the x-axis. We're getting the angle between the weight force and the slope, or the x-axis, so it's 65 degrees instead of the given 25 degrees. Right? Doing the calculation gives you 240 newtons. And similarly, for the y component of the weight force, the same mass, the same acceleration, the same angle, except that this time is a sine, it's a sine function, giving you a weight force of 550 newtons for the x and y, for the y component. All right, does that make sense for why we tried to figure out the angle between the weight force and the slope, and then we use that angle to get the x and y components? Right, very good. I can see some thumbs up there. So once we now have the X and Y components for the weight force, we can now solve for the acceleration. So notice we assigned the acceleration to be along the slope, and we said that the slope, that will be our x-axis. So that means we're getting the acceleration along the x-axis. So we write Newton's second law of motion along the x-axis. Net force along the x should be equal to the mass times acceleration along the x. So let's do the left-hand side, net force. Look at your free body diagram. You have two forces along the x. You have frictional force that's to the left, weight force, x component of the weight force that's to the right. So you have x component should be positive, and then frictional force should be negative. So that's the left-hand side of Newton's second law of motion. The right-hand side is just carried over as mass times acceleration. Okay. We want to find acceleration, so we have to isolate acceleration. We need to get rid of mass. Okay. So we divide both sides by mass, and we have the left side, x component of weight minus force, divide that by the mass. And we know everything. We've solved for the x component of the weight force. We solved that earlier. Frictional force was given to be 70 newtons, and the mass of the skier who goes down the slope is 58 kilograms, what was also given. And so you can find the acceleration down the slope, which is what we assigned to be the x-axis. Right. Okay, any question about this example, or does the solution make sense? Why? So it's really just a recipe. It's a recipe of drawing the free body diagram, okay, figuring out whether you want to do the x component of Newton's second law of motion or the y component, depending on what's being asked in the question. Getting the net force along the horizontal or along the vertical, and then finding whatever you want to find based on the question. All right, so that essentially wraps up the lecture. Unless there are any questions, we can proceed to the workshop. Yeah, all right, so I don't see any questions in the chat box, but if you think of a question, feel free to pop it in there anytime. All right, so as usual, I'll give you some time to do the workshop. I think we can do the discussion at 11:30. So that's about 30 minutes for you to do the workshop, or attempt doing it, looking at the problems. And then we'll look at the solutions at 11:30. Does that sound like does that sound all right? Good. Thanks for the thumbs up, for the confirmation. Okay, I'll stop